Welcome to Simbeor. We develop and distribute Simbeor electromagnetic signal integrity software. This is a demo of currents and power flow in differential viaholes. For this demo I will use differential viaholes from SMP28 validation platform from Wild River Technology. Differential vias are located here and were analyzed in post-layout with post-layout analysis in Simbeor. With models for transmission lines constructed with Simbeor 3D solver and models for viaholes constructed with Simbeor 3D THz solver. The geometry was extracted into a circuit with discontinuities here. And discontinuities separately extracted and simulated in this particular case with Simbeor 3D THz solver. Those are vias. It is very important that Simbeor is validated with measurements, and here we can see how the measurements correspond to the analysis. Curves A are measurement and curves B are simulation, and this is magnitude of the reflection S11 as differential reflection and differential transmission or insertion loss. This is group delay, overlaps simulated and measured, and this is phase delay, also overlaps, and this is TDR of the structure. Differential TDR, again, A is measurement, B is simulation, very close. So let's take a look at the currents and power flow in the viaholes. There are some fields pre-computed here, and first we will take a look at the current flow. Current density, surface current density at 1 GHz. I turn it on and we can see how currents flowing through the vias. It's the source here located at the bottom, 1 volt in series with 50 ohm for this port and minus 1 volt magnitude, or it's that provides again in series with 50 ohm, that provides differential excitation here. Technically it's 100 ohm in series with 1 volt here, and we see currents flowing back and forth in opposite direction, but also fair amount of currents flowing on the planes. And current is in dB and normalized to relative to this maximal value of the current. So to see it closer, we can restrict the area, visualization area, a little bit to not see the this area with whether there is transition from the sources to differential mode, like this. And now we can see how currents flowing on top surface here. Oh, let's start from the bottom side. You can see how currents are flowing nicely, getting into vias. On the other side of the plane, currents are flowing in different pattern, and then you can see through the vias and to the top, and they are kind of going through those structures. Notice that there is some current flowing on the stitching vias and no currents flowing on the sidewalls that are electric conductors here, perfect electric conductors. Current density at 10 GHz. There is not much change, except that now we can see kind of wave-like behavior. It works almost as a transmission line. More currents flowing on stitching vias. And again, currents are perfectly kind of one direction, another direction. Then return current flow on top. Right here we see the distribution of the currents on the planes, and some current gets through get back through the stitching vias. (32.5 gigahertz). More currents flowing outside of this area, farther and farther. So they are relatively kind of small, but now we can see currents flowing on the side walls, very small also, in blue, about minus 60 dB comparing to the maximum value. And more wave-like behavior here again. Okay, and 43.85 gigahertz, and now currents are not localized, and that's why we see considerable discrepancy in the insertion loss at those frequencies. The via loses the localization, so essentially it's not behaving as at 1 gigahertz obviously, and the energy is spread farther away, and we can see the return currents flowing on the sidewall. In reality they're just going through something else on the board. That is really difficult to predict with 3D analysis. And compare it to 1 gigahertz, you can see it really kind of striking difference in behavior. What about the power flow? At 1 gigahertz, again logarithmic scale relative to maximal value in watt per square meter. We can see that the power from the bottom side, it gets in the same direction. You can see the current was flowing in the opposite direction, but right here you can see that power flow under both strips in the same direction. It's for differential line, and then it gets into this area, into this antipod, get to the other side of the antipod, spreads a little in this area, and then recombines into this or gets into the next antipod. But overall we can see it's VS behaving as almost as a short segment of transmission line. On the other end we have some kind of defects of layout, but in power it just flows around those. You can see it. And to the other end, 10 gigahertz. 10 gigahertz we can see that energy is spreading a little bit farther from VS, so we can see this flowing around a little and more wave-like behavior. 32 gigahertz. You can see that power gets and bounces from the stitching vias on the sides. And non-localized case, power spreads all around here and bounces back from the side walls. Oh, it's like this. You can see it flowing sideways almost here, and basically becomes unpredictable. This case becomes unpredictable. And again, comparing to 1 gigahertz, that's again striking difference in behavior of VS, localized case and unlocalized case. In Simbeor, with Simbeor 3DTF, I can also compute power stored and this is in watts per cubic meter computed for each element and divided by volume, and we can see that again stored energy is located mostly in this area around differential Vs. This is restricted by minus 30 dB view, 10 gigahertz. 32.5 gigahertz, and we can see more energy around those teaching vias on the side. And finally, unlocalized case of 44, about 44 gigahertz. You can see energy stored in larger, much larger area around vias. This is the end of this demonstration. To learn more, visit Simbeorian.com. Application notes, webinars, and knowledge base sections. Or download and try Simbeor now. It is available in download section. Thank you.